All right, here's our next section. This is 6.11 in our workbook, and this is called Integration by Partial Fractions. What we have here is a pretty useful tool in order to deal with something in integration when we have something to integrate that we don't quite know what to do with, or we don't have necessarily the tools to be able to do with this. We're going to use a separate tool to change our integration question to something simpler. And this goes back to long division, and so we have to remind ourselves how we do this. And if we're dividing 3x cubed plus x squared minus 1, dividing that by x plus 2. So when we set up long division with this, remember we start with our divisor is x plus 2. Here's our division sign. Usually it's a good habit when we have a polynomial in our dividend that we have each term represented. And notice that there's no x terms here, so let's call that 0x and leave room for that. And then we start off with dividing. X goes into 3x cubed, 3x squared times, multiplying that back by our binomial, makes this 3x cubed, makes this one plus 6x squared. And when we subtract, please pay attention to subtracting. If we had negatives in here, be aware with that. This ends up being minus 5x squared. This is why we have that plus 0x term in here, and this ends up being minus 5x is our next term. Negative 5x times x is negative 5x squared. Negative 5x times 2 is minus 10x. And when we go to subtract, this ends up being plus 10x minus 1. Our last term in our quotient will be plus 10. We multiply that by our binomial, and we get plus 10x plus 20. We go and subtract, and we get negative 21 for our remainder. Our division statement says, therefore, the question as it was posed, or this rational expression, is actually equal to our quotient, which is 3x squared minus 5x plus 10. And then our remainder ends up being minus 21 over x plus 2. Our remainder divided by our divisor. A couple questions of review of what to do with this when you have some integration of some fairly straightforward looking pieces here. We have the integral of 1 over x plus 3 dx. So this just ends up being natural log of absolute x plus 3. We can't forget about the plus c on here. Whether or not you do that with a substitution at this point, these ones are not too bad. You could do it with a substitution if you wanted to. We could also do it by recognizing the fact that 1 over x minus 1 squared is x minus 1 to the negative 2 dx. And when we integrate that, that ends up being 1 over x minus 1. We take our exponent of negative 2 and we add 1 to it. Is an exponent of negative 1. And then we also divide by negative 1. So this ends up being the negative of 1 over x minus 1 plus c. Number 3, also pretty straightforward, not too bad. This just ends up being equal to, we have natural log of the absolute value of 2 minus 3x. But we're also going to divide by the derivative of that inner function, so negative 1/3 natural log 2 minus 3x plus c. So these aren't too bad, but when we get to this part, 1 over x squared plus x minus 2. We don't know what to do. We recognize the fact that this ends up being 1 over x plus 2, x minus 1. We could call it that. But with product rule, this ends up being really tricky to do anything about. So at this point, we are at a loss. At which point we bring in this new method that's going to be called partial fractions. So we're going to look at a couple of different types of what this is, and this goes back to rational expressions and doing some operations with rationals. And it goes back to 2 over x minus 1 plus 3 over x plus 2. We have a common denominator of x minus 1 times x plus 2. This first term of 2 in the numerator needs to be multiplied up and down by x plus 2 to get a common denominator. The second term, to get a common denominator of 3, ends up being multiplied up and down by x minus 1. When we distribute this, 2x plus 4 plus 3x minus 3, this is all over still x minus 1, x plus 2, ends up being equal to 5x plus 1 over x minus 1 plus 2. So what that means is if we're given something like this, somehow you should be able to break it apart into two rational expressions, and so probably going to be a little bit easier to integrate. So this one right here, hard to integrate. This one right here, a lot easier. What's tricky is to go through this process this way, but it's doable. So in this case, we've got an integral of some numerator divided by x minus 1, x plus 2. We want it to be equal to an integration of some numerator over x minus 1 plus another numerator over x plus 2. We want to break it apart into these things. So in this case, if we have the integral of 5x plus 1 over x minus 1, x plus 2. So if 5x plus 1 is our numerator, what we do is we say that it's equal to some value a over x minus 1 plus some value b over x plus 2. We don't quite know what those look like yet. We don't know what numbers are going to fall in for a and b, but we do know that we can distribute. So on the left side, if we multiply, on the left side we have 5x plus 1. We multiply by the LCD, and this a ends up being a times x plus 2. The b ends up being multiplied b times x minus 1. The denominators divide away. And now, if we expand on the right side, we have 5x plus 1 on the left is equal to ax plus 2a, just distributing. And then when we reorder things, on the left side we have 5 x's, and we have a constant of 1. If we collect our x terms, we have a plus b x's. And what do we have for constants? Plus 2a minus 1b. So from that, we can conclude that this term, the coefficient in front of your x, is going to be this. And we can also conclude that our constant term is going to be this one here. So therefore, 5x is equal to a plus b times x, and our constant is 1 is equal to 2a minus 1b. So we need to solve our system of equations. We have two equations and two unknowns, because really that x isn't relevant to that first one. We have this system that looks like this. 5 is equal to a plus b from our first, and 1 is equal to 2a minus b. Here's equation 1, here's equation 2. This one is set up quite nice for elimination, in that we have positive b, positive 1b, and negative 1b. We can just add these down, and this ends up being 6 is equal to 3a, and the b's eliminate. And this is just equation 1 plus equation 2. So therefore, a is equal to 2. Once a is 2, we're going to substitute that into our first equation. 5 is equal to 2 plus b. Therefore, b is equal to 3. We have our two parts of our solution. And so therefore, this integral of 5x plus 1 over x minus 1x plus 2 is equal to 2 is your a value, 2 over x minus 1 dx, plus 3 over x plus 2 dx. Each of these are much easier to integrate now, and so we end up with an answer of 2 natural log absolute x minus 1 plus 3 natural log absolute x plus 2, and don't forget our plus c. Type 2. So if type 1 was the degree of our numerator is less than the degree of your denominator, type 2 ends up looking like this if we have repeated linear factors. If we have an x minus 3 squared in your integration, if we have something that looks like this, we're going to break it apart into x minus 3 to the 1 and x minus 3 to the 2 as our two terms. In this example, we're just going to simplify this and go backwards like we would have done through 20-1, and we're going to get a common denominator here. This ends up being 3 bracket x minus 3 over x minus 3 squared plus 4 over x minus 3 squared. So in this case, when we have an integration that looks like this, x minus 3 squared, we're going to break it apart. We're going to want to break it apart into these two terms. In our next step, what do we have? We have 3x minus 9, 4 over x minus 3 squared ends up being equal to 3x minus 5 over x minus 3 squared. So what we end up with is, if we have this original question of 3x minus 5 over x minus 3 squared, we want to break it apart into, one of them has a denominator of x minus 3, the other denominator is going to be x minus 3 squared. So let's go from here. Let's go from 3x minus 5 if we were given this as the question. Let's write that denominator as factored. And it's going to be equal to some number a over x minus 3, some other number b over x minus 3 squared. So we recognize 3x minus 5 on the left, multiplying everything through by your LCD. A is multiplied by x minus 3, b is just b times 1. And we end up with 3x minus 5 is equal to, let's distribute, ax minus 3a. This is just b. And so what we have is 3x plus negative 5 is equal to our, let's group our terms together. Our x is just ax, and our constant term ends up being plus negative 3a plus b. So we can conclude that, well, let's look at our x terms, really pretty straightforward. Our constant terms is going to be these, and we end up with 3 is equal to a, and negative 5 is equal to negative 3a plus b. And so we want to solve this system of equations, and our system looks like this. Actually, a little more straightforward with this one. Is equal to a is our first equation. Negative 5 is equal to negative 3a plus b is our second equation. So we can just substitute, and we end up with negative 5 is equal to negative 3. Substitute our value of a is 3. Plus b, we add 9 to both sides. 4 is equal to b. Therefore, our integral of 3x minus 5 over x minus 3 squared, we found that a was 3, and we found that b is 4. And so that's how these break apart. Integral of 3 over x minus 3 dx plus integral of 4 over x minus 3 squared dx. And this ends up being quite a bit simpler to do. Our first one ends up being 3 natural log of x minus 3. Our second one ends up being, because this is x minus 3 to the negative 2, we add 1 to the exponent, and this ends up being minus 4 over x minus 3. And let's see. But the only problem with non-repeated irreducible quadratic factors, like this x squared plus 1, if we have something like this, this ends up being a little bit more complex than we are going to deal with in this course. That leads to inverse trig functions like tan inverse, and we're not going to deal with that right now. Part 3. If our degree of our numerator is greater than or greater or equal to the degree of the denominator, so if it's the same or more, let's divide first. Let's do this as division and write it as a mixed fraction. So x minus 7 into x plus 5. This ends up being 1 times x minus 7 is x minus 7, of course. Subtract, we get 12. So this ends up being equal to 1 plus 12 over x minus 7. So our integral ends up being the integral of x plus 5 over x minus 7 ends up being the integral of 1 plus 12 over x minus 7, all dx. We break that apart. This ends up being the integral of 1 dx plus the integral of 12 over x minus 7 dx. No big deal. We integrate the 1, it's this. We integrate 12 over x minus 7, it is plus 12 natural log of x minus 7 in absolute. So when the degrees are equal, this is what we're going to do. Ends up being quite straightforward. If the numerator is greater, we start off with long division. This is where I would personally prefer to write out each of the terms. So 3x cubed plus 0x squared plus 0x minus 8 when we do our division. And then x squared goes into 3x cubed. 3x times, I multiply that back into the binomial, gives me 3x cubed. And then just make sure that we line up each of our like terms. 3x times -4 is minus 12x. So let's write this underneath the 0x. When I subtract, this leaves me with 12x. I bring down my -8, and that ends up being our remainder. So therefore, this ends up being equal to our quotient, which is 3x, plus our remainder, 12x minus 8, over our divisor, which is x squared minus 4. So our integral of 3x cubed minus 8 over x squared minus 4 ends up being equal to the integral of 3x plus 12x minus 8 over x squared minus 4. That second part of 12x minus 8 over x squared minus 4 becomes our partial fraction. And so therefore, let's see what we have here. We've got 12x minus 8 over x squared minus 4. If we factor that denominator, it's a factor of x plus 2 and x minus 2. So therefore, x minus 8 is equal to a times x minus 2 plus b times x plus 2. And when we multiply this out, 12x minus 8 ends up being equal to, we have ax minus 2a plus bx plus 2b. Leaves us with 12x minus 8. Now let's group our x terms. We have a plus b for our x coefficient. We have negative 2a plus 2b for our constant. Therefore, we can conclude that 12, our coefficient on x, is equal to a plus b. Constant of negative 8 is equal to negative 2a plus 2b. And there's our system of equations. Equals a plus b, negative 8 equals negative 2a plus 2b. Equation 1, equation 2. Probably the easiest way to deal with this is just take equation number 1 and double it. 24 is equal to 2a plus 2b. And then if I add those down, this ends up being 16 is equal to 4b. The a's eliminate. B is equal to 4. Substituting this in, 12 is equal to b plus 4 is equal to 8. Using those two amounts, let's go back up here to our integral. Don't forget about the first piece of our integration, which was just 3x. There's that quotient up above. So our integral breaks into 3x plus 8 over x plus 2 dx. That was our a value. And then our b value made this 4 over x minus 2. We integrate each of those pieces. 3x becomes 3x squared over 2 plus 8 ln absolute x plus 2 plus 4 ln x minus 2 plus c. We'll just do that in one step. And that is it. If you have any questions, please feel free to ask, and good luck.